Welcome back. We are now beginning week 7 materials for Math 1650D Precalculus, and that corresponds to the latter half of section 4 of our textbook. Properties of logarithmic functions, that's where we are going to begin, but it's not going to hurt to do a little bit of review, so let's do a little bit of review. What is an exponential function? The kind of functions like these given by y equals a to the x power, and this picture shows you the graphs of exponential functions for various a values. When a is greater than 1, as you can see in this blue, red, and brown graph, a value is 2, 3, and 10 respectively. We have increasing and increases faster as a goes bigger. When a is less than 1, like purple, green, and kind of yellowish gold curve is showing, where a values are 1/2, 1/3, and 1/10 respectively, we have decreasing graphs, and decreases faster when a is smaller. As you can see, if you look at each individual graph, it clearly passes the horizontal line test, which means the function is invertible and we can define an inverse function. And that inverse function is a logarithmic function. And that's how we define that's how we define logarithmic function from an exponential. Now, what are the graphs of exponential and logarithmic function? They are inverse, so we have to have this symmetric relation with respect to the principal diagonal, and same is true even when a value is less than 1. The special case that is particularly interesting is when a value is a mysterious transcendental irrational number e, which is approximately 2.718 something, which has graphs kind of like this one. And in this case, we define the exponential and logarithmic functions as the natural exponential and the natural logarithmic functions. Okay, now that we had a brief reviews on everything, let's talk about the properties of logarithmic functions, or simply log rules. And we have two types of log rules, and the second log rules are the typical log rules. Log functions change multiplication into addition, division into subtraction, and power into coefficient. That's what the log functions do. Just for arbitrary a. For special cases, when a is e, then we have natural log ln, but the rules remain exactly the same. And why are they true? In order to prove those, let's make a little bit further observations, a little bit more observations, which are log rules 1. First, cancellation rules. Log of exponential is just a, because log and exponential cancel each other out because they are just inverse of each other. Likewise, natural log and natural exponential e cancel each other out. And also vice versa, exponential and then log just cancel each other out. This and that cancel each other out. And same goes to natural log and natural exponent. And they're just inverse functions, so there's nothing to prove. Now how about these? Log of 1 is always 0, log of a and base are the same than 1, and natural log of 1 is 0, and natural log of e is 1. Well, the easiest proof I can think of is this. 1 is nothing more than a to the 0 power, and a is the same a that we have in the base. So after cancellation, this a down there and then this log of a cancel out, and then we have 0. How about the second one, log a of a? This a is nothing more than a to the first power. So after cancellation, we just have 1. The cancellation are 4.1 a and b. They are just inverse functions. So inverse and original function cancel each other out. Now let's use those to answer the log rules. How do we do that? Let's start from the right hand side. log of a of x plus log of a of y, and then let's take the exponential. Let's increase the font so that you can read this one a little bit better, and then take the exponential a to that. And then what we apply, let's apply exponent rules, because we have the same base. We have a to this power and a to that power. We just use exponent rule. And then let's apply the cancellation rule. A to certain power and the log of a, they just cancel each other out. We get just x. Likewise, we get y. So what do we get? A to this sum of this logarithm is x times y. Now let's take log of a of both sides, and right hand side is log of a of x times y as desired, and the left hand side is log of a, and then a to that cancel each other out, and we have desired result. So we just use this cancellation rule and exponent rule to prove it. How about the next rule? It's gonna be pretty much the same deal. Start from the right hand side and then use this exponent rule to change the subtraction of the power into division. And after using cancellation rule, log of a up there and exponential cancel out, we just have x, and likewise we have y, so we have x over y. Now preparation is done. Let's take log of a of both sides. That's gonna kill off this a in the left hand side, and then we have just log minus log. Right hand side is log of x minus y, x over y, excuse me. How about the power? That's actually much easier than the other two. Not much easier, a little bit easier than the other two, but the idea is the same. Start from the right hand side and then just apply the exponent rule and then cancellation rule. Take the log again, and then we will have the desired answer. And we can repeat the same thing for special case a is e, then you're gonna get log rules for natural logarithmic functions. Now, are you ready to apply these log rules to some application problems? Well, ready or not, let's go. Let's express some complicated log expression into a single logarithm. How do we do that? Usually, rule number 3, log rule c first, and then apply a and b together in the same step. Let's go with the easiest example. This 3 goes up to the exponent. This 2 goes up to the exponent. So we just use rule number 3, log rule c, and then apply a. There's no subtraction, so just apply a. Sum of logarithm becomes product inside that logarithm. How about the next example here? We have some mixed logarithm. Let's just move on to even more complicated one here. We have some mixed expression here, u v x, but if you follow the same strategy, you can handle this with ease. Rule c first and get rid of all the coefficient and apply a and b at the same time. How do we do that? Rule c first, so log of 2 log of u just become log of u squared. 1/2 log of v becomes log of 1/2 power. And then 3 log of x squared, 3 goes over there, so we have x to the 6th power. 2 log of 2x, so we have 2x to the 2nd power, which is 2 squared is 4x squared. And then what we do, we just apply rule a and b, rules a and b simultaneously. Sum of logarithm becomes product, subtraction becomes quotient, which means if you have any kind of addition, that's multiplication, so that goes to numerator. If you have any subtraction, that's division, that goes to denominator. So all plus goes to numerator, all minus goes to denominator. And I did some color coding to help myself out here. The same thing with some color coding. Log of u squared, that's positive coefficient, so blue, that's going to numerator. And that's negative, so red, that's going to denominator. Blue, numerator, that's plus. Minus, that's going to denominator. And put those together using rule A and B together at the same time. After simplification, we get something like that. Let me increase the font so that you can read these fractions a little bit better. It's going to be a lot more efficient to apply rule A and rule B at the same time rather than applying each of them one at a time using, what do you call, each pair at a time. That's going to make the problem too complicated. What if we have some problem like this one? Well, again, the same deal. Move all the coefficient to the power and then apply the rule A and rule B simultaneously. That's what we do. Move this 1/2 power to the power, 1/2 in coefficient to the power, this 1/2 to the power, and we have square roots like these. And then apply the rule A and rule B simultaneously. All positive go to numerator, all negative go to denominator. Afterwards, it's just a simplification. And you can go backwards too. In this case, log of x is A, log of y is B, log of z is C, and then express the given logarithm with A, B, and C. A, B, and C. How about something like this? We just apply all those log rules backward. So numerator will become positive, denominator will have negative. So we can decompose the numerator into plus, plus, minus, minus. And then put those powers out up front. And we have something like these. And then replace log of x, log of y, log of z as A, B, and C respectively, and that's it. That kind of thing is log rules. And in this notebook, I didn't bother writing any problem about log of arbitrary base or log of base 10. That's because in calculus, you hardly use any of those logs. And I believe almost everybody here, perhaps everybody here, is headed toward calculus 1. So I find really no more motivation to deal with any other base. I'm going to stick to ln most of the time.